Picture this: a star, not unlike our own sun, reaching the end of its life. Its outer layers begin to shimmer, then erupt in a dazzling explosion of light, painting the cosmos in hues of gold, crimson, and violet. For a brief, breathtaking moment, it outshines entire galaxies. This isn't just the end of a star, it's a cosmic rebirth, a transformation that sends ripples through the fabric of space itself. What happens when a star dies? The answer is far more extraordinary than most of us could ever imagine. Stellar death isn't just an ending, it's a spectacle that shapes the universe, forging new elements, birthing black holes, and even paving the way for life itself. Across the vast expanse of space, stars meet their fates in wildly different ways. Some go out with a whisper, collapsing into dense, dark remnants, while others explode with such ferocity that their light echoes across billions of years. These cataclysmic events are more than just cosmic fireworks. They're the engines of creation, scattering the building blocks of planets and even life across the cosmos. And yet, for all their power, these processes remain some of the most enigmatic in the universe. How can something so destructive also be so essential? That's the mystery we're about to unravel. In this journey, we'll explore 18 unique perspectives on the end of celestial life, from the violent beauty of supernova to the eerie pull of black holes, from the slow fade of white dwarfs to the explosive collisions of neutron stars. Each of these deaths tells a story, not just about the stars themselves, but about the universe's grand, interconnected dance. By the time we're done, you'll never look at the night sky the same way again. Because when a star dies, it doesn't just vanish, it leaves behind a legacy that shapes everything we see and everything we are, ready to uncover the secrets of star death. Let's begin. Among all the ways a star can meet its end, few are as spectacular or as influential as a supernova. Imagine a star 20 times more massive than our sun, burning through its fuel at a furious pace. For millions of years, it fights a losing battle against gravity, fusing heavier and heavier elements in its core until it can no longer sustain the delicate balance. Then, in a fraction of a second, the core collapses. The outer layers, no longer supported, come crashing down with unimaginable force, only to rebound in a shockwave so powerful it tears the star apart. The resulting explosion can outshine an entire galaxy for weeks, releasing more energy than our sun will emit in its entire 10 billion-year lifetime. This isn't just a hypothetical scenario. In the year 1054, Chinese astronomers recorded a guest star in the constellation Taurus, so bright it was visible even during the day. That was the birth of the Crab Nebula, the remnants of a supernova whose light reached Earth nearly 1,000 years ago. Today, we understand that these explosions are cosmic forges, scattering elements like iron, gold, and uranium into space elements that would one day form planets, oceans, and even the blood in our veins. Without supernova, the universe would lack the raw materials for life as we know it. But the story doesn't end with the explosion. The shock waves from a supernova can trigger the birth of new stars, compressing nearby gas clouds until they ignite. The Crab Nebula itself still pulses with energy. Its spinning neutron star, a dense remnant no larger than a city, sending out beams of radiation like a cosmic lighthouse. These echoes of stellar death remind us that destruction and creation are two sides of the same coin. Every time we look up at the night sky, we're witnessing a universe shaped by these violent, beautiful endings, a cycle as old as time itself. While supernovae scatter the ingredients for new worlds across the cosmos, some dying stars leave behind something even more extraordinary, a neutron star. Imagine taking the entire mass of our Sun and crushing it into a sphere no wider than Manhattan. The result is so dense that a single teaspoon of its material would weigh billions of tons on Earth, a mind-bending reality where the rules of physics as we know them warp under unimaginable pressure. These cosmic remnants are born from the collapse of massive stars, their cores squeezed so tightly that protons and electrons fuse into neutrons, leaving behind a city-sized object with the gravity of a black hole and the magnetic field of a trillion refrigerators. Among the most fascinating neutron stars are pulsars spinning beacons that flash like lighthouses in the void. Rotating hundreds of times per second, their jets of radiation sweep across space with such precision that astronomers use them as cosmic clocks. In fact, the discovery of the first pulsar in 1967 was so baffling that scientists briefly nicknamed it Little Green Men 1, mistaking its rhythmic signals for an alien transmission. Today, we know these celestial metronomes are far more valuable than science fiction. Their impeccable timing has allowed us to test Einstein's theory of general relativity with unparalleled accuracy, confirming predictions about how gravity bends spacetime itself. But the true revolution came in 2017 when astronomers detected something unprecedented: the collision of two neutron stars. The event sent ripples through space-time called gravitational waves, while also unleashing a fireworks show of light, gold, and platinum across the universe. This single observation opened an entirely new way to study the cosmos, proving that neutron star mergers are cosmic gold mines literally. These violent encounters forge heavy elements like gold and uranium in their aftermath, scattering them into space where they may one day become part of new planets or even jewelry on Earth. Neutron stars remind us that death in the cosmos is never truly an end. From their unfathomable density to their role as laboratories for extreme physics, they challenge our understanding of reality while quietly shaping the universe's future. Whether as pulsars keeping time across the ages or as colliding factories of precious metals, these stellar ghosts continue to influence the cosmos long after their birth in catastrophe. And as we listen to their gravitational whispers and observe their brilliant aftermath, one thing becomes clear: the universe writes its most profound stories in the remnants of the dead. If neutron stars push the limits of density, black holes shatter them entirely. These are the universe's ultimate enigmas, where gravity wins its final victory. When a star dozens of times more massive than our Sun exhausts its fuel, its core doesn't just collapse, it implodes with such force that not even light can escape. The boundary of no return, known as the event horizon, marks the point where the pull becomes irreversible. Picture it like a waterfall's edge. Once you cross, there's no swimming back. But the real nightmare begins just beyond that threshold with a process called spaghettification. Imagine falling feet first toward a black hole. The gravitational tug on your toes becomes infinitely stronger than on your head, stretching you into a thin, noodle-like strand, a cosmic noodle, if you will, before you're crushed into oblivion. Yet black holes aren't just destructive monsters. Thanks to Stephen Hawking's groundbreaking work, we now know they slowly leak energy over eons, evaporating through a quantum quirk called Hawking radiation. Here's the paradox: as a black hole radiates away, the information about what fell into it, whether stars, planets, or unfortunate astronauts, seems to vanish forever, violating a fundamental law of physics that states information can't be destroyed. This information paradox has haunted scientists for decades, hinting that our understanding of reality might be incomplete. Even stranger are the theories suggesting black holes could be portals, not tombs, but tunnels to other universes or distant corners of spacetime. Some equations in general relativity allow for the existence of wormholes, shortcuts through the cosmic fabric, though no evidence exists yet. Could a black hole singularity tear a hole in spacetime itself? Or are they truly the end, where matter and time cease to have meaning? The answers might lie in a theory that unites gravity and quantum mechanics, a puzzle that continues to challenge the brightest minds. What we do know is this: black holes shape galaxies, bending the paths of stars around them like invisible puppeteers. The supermassive one at our Milky Way's heart, Sagittarius, a star, sits quietly now, but its appetite could awaken anytime. From devouring stars to warping the very flow of time, black holes remind us that the universe's most profound mysteries often lurk in the darkest places. And as we peer into their abyss, we're not just staring at death, we're glimpsing the edges of human knowledge itself. While black holes and neutron stars dominate the cosmic stage with their dramatic final acts, not all stars meet such explosive ends. Take our own sun. Its future is far quieter, though no less profound. After billions of years of steady fusion, it will exhaust its hydrogen fuel, swelling into a red giant that engulfs Mercury and Venus before gently shedding its outer layers. What remains won't be a supernova or a singularity, but a dense, Earth-sized ember called a white dwarf. Imagine a teaspoon of its material. It would weigh as much as an elephant, crushed into a crystalline structure by gravity so intense that only quantum physics keeps it from collapsing further. These stellar remnants glow faintly with leftover heat, like cosmic coals cooling in the void. Unlike their massive counterparts, white dwarfs fade slowly, taking trillions of years to dim completely into theoretical black dwarfs, cold, dark husks that may not even exist yet, given the universe's current age. Our sun's destiny lies along this path, a silent fade into obscurity, but don't mistake silence for irrelevance. White dwarfs serve as celestial time capsules, preserving clues about the chemical makeup of ancient stars in their atmospheres. Some even crystallize into diamond-like structures over time, turning into literal cosmic jewels. Yet there's a twist in this quiet tale. When a white dwarf orbits a companion star in a binary system, it can steal material from its neighbor, piling it onto its surface until a runaway nuclear reaction ignites. The result, a type Ia Supernova, an explosion so uniform in brightness that astronomers use these events as standard candles to measure vast cosmic distances. It was observations of type Ia Supernova that revealed the universe's accelerating expansion, hinting at the mysterious force we now call dark energy. From silent fade-outs to precision cosmic yardsticks, white dwarfs prove that even the gentlest stellar deaths leave fingerprints on the universe. They remind us that destruction isn't always violent, and that sometimes the quietest endings illuminate the cosmos in ways explosions never could. Whether as future relics of our solar system or as tools to map the invisible fabric of spacetime, these fading embers are anything but insignificant. Among the universe's most breathtaking farewells are the planetary nebulae, celestial masterpieces sculpted by dying stars. Picture a sun-like star in its final throes, gently puffing away its outer layers in shimmering waves of gas and dust. These expelled shells, illuminated by the star's exposed core, glow in vivid hues of electric blue, deep red, and emerald green, twisting into delicate rings, spirals, or even butterfly-like wings. The Ring Nebula, one of the most famous, floats like a luminous smoke ring in space, its intricate structure revealing the subtle interplay of stellar winds and radiation. But don't let the name fool you. Planetary nebulae have nothing to do with planets. 18th century, astronomers coined the term because their round shapes resembled distant gas giants through primitive telescopes. Today, we know them as the final brushstrokes of stars like our Sun, painting the cosmos with their dying light. What makes these nebulae truly remarkable isn't just their beauty, it's their role as cosmic recyclers. As the star sheds its outer layers, it flings heavy elements like carbon, nitrogen, and oxygen into space elements forged in its core over billions of years. This stardust becomes the raw material for new stars, planets, and even the molecules that make up life. The carbon in your DNA, the oxygen in your lungs, the calcium in your bones, all were once scattered into the void by events like these. Planetary nebulae are nature's way of turning death into rebirth, ensuring that every ending fuels a new beginning. The Hubble Space Telescope has been our window into this celestial artistry, capturing details so sharp they resemble watercolor paintings. From the ethereal glow of the Helix Nebula, nicknamed the Eye of God, to the bipolar jets of the Butterfly Nebula, these images blend science and art, reminding us that the universe thrives on both precision and creativity. Hubble's observations have even revealed surprises, like the intricate knots of gas in the Cat's Eye Nebula, each one larger than our solar system, twisting in patterns we're still struggling to decode. Yet these luminous shrouds are fleeting. Within tens of thousands of years, a blink in cosmic time, the gas disperses. The central star cools into a white dwarf, and the nebula fades from view. We're witnessing a transient phase, a celestial firework caught mid-burst. That ephemeral quality makes every Hubble snapshot a priceless fossil, a glimpse into a process that shapes the chemistry of galaxies. So the next time you gaze at a planetary nebula's delicate filaments, remember, you're not just seeing a star's death. You're witnessing the universe's grand recycling program, where beauty and purpose collide in a swirl of stardust. If neutron stars are the universe's dense, spinning lighthouses, then magnetars are their volatile, magnetic cousins, cosmic powerhouses that rewrite the rules of physics. Picture a neutron star, already mind-bending in its own right, then amplify its magnetic field 1,000-fold. The result is a magnetar, where magnetic forces are so intense they could strip the data from every credit card on Earth from halfway across the galaxy. These objects are so extreme that if you ventured within 1,000 kilometers of one, your atoms would stretch into thin, magnetized ribbons before disintegrating entirely. The true terror of a magnetar lies in its sporadic eruptions. In 2004, a flare from a magnetar 50,000 light-years away, far outside our Milky Way, still managed to compress Earth's ionosphere, distorting radio signals worldwide. For a fraction of a second, it outshone the full moon in gamma rays, despite being farther than the farthest stars visible to the naked eye. Astronomers call these events starquakes, where the magnetar's crust, strained by twisting magnetic fields, snaps like an over-tightened violin string, releasing energy equivalent to 1 billion megaton bombs. How do these monsters form? The leading theory suggests they are born from the most chaotic stellar death supernova, where the collapsing star's magnetic field becomes trapped and amplified in the spinning core. It's like winding a cosmic rubber band until it hums with pent-up energy. Some magnetars might even start as fast-spinning neutron stars, their magnetic fields growing stronger as their rotation slows over centuries. What's certain is that they don't last forever. Within 10,000 years, a blip on cosmic timescales, their magnetic fields decay, leaving behind an ordinary neutron star. But magnetars might hold the key to one of astronomy's biggest puzzles: fast radio bursts. These mysterious, milliseconds-long blips of radio energy have baffled scientists since their discovery. Some seem to repeat while others vanish without a trace. In 2020, a magnetar in our own galaxy emitted a burst eerily similar to these cosmic signals, suggesting at least some could originate from these magnetic behemoths. Whether they explain all fast radio bursts remains uncertain, but one thing's clear: magnetars prove that even in death, stars can unleash forces beyond our wildest imagination. From reshaping planetary atmospheres to potentially powering intergalactic signals, they remind us that the universe's most violent actors often hide the most profound secrets. Among the universe's most violent farewells, hypernovae stand in a league of their own, stellar explosions so powerful they dwarf even supernova. Picture a star at least 30 times more massive than our Sun, its core collapsing not into a neutron star but directly into a black hole. The energy released doesn't just tear the star apart, it funnels into twin jets of plasma screaming outward at nearly the speed of light. These jets, packed with gamma rays, can outshine an entire galaxy for mere seconds, yet their impact echoes across cosmic history. The true terror of a hypernova isn't just its brilliance, it's the gamma ray burst that follows. These bursts, the universe's most luminous electromagnetic events, are so focused that if one occurred within a few thousand light-years of Earth, its radiation could strip our ozone layer, triggering mass extinctions. Evidence suggests this might have happened before. A gamma-ray burst, possibly from a hypernova, may have contributed to the Ordovician extinction 450 million years ago, wiping out nearly 85% of marine life. The universe, it seems, doesn't just create life, it occasionally threatens it with stellar fireworks. To study these cosmic explosions, scientists rely on missions like NASA's SWIFT satellite. Launched in 2004, SWIFT acts as a celestial watchdog, spinning in orbit to detect gamma-ray bursts within seconds of their occurrence. Its rapid alerts let telescopes worldwide pivot to observe the afterglow, a fading fingerprint of the explosion's chemistry. Some of these bursts originate from galaxies billions of light-years away, making them time capsules from the universe's infancy. The farthest yet detected, GRB 090423, erupted just 630 million years after the Big Bang, offering a glimpse into an era when galaxies were first assembling. What makes hypernova truly transformative is their role in cosmic chemistry. The same jets that threaten nearby worlds also forge elements like platinum and gold in their fury, scattering them into space. Without these cataclysms, the universe might lack the heavy elements essential for planets or life. Even their black hole remnants shape galaxies, their gravity influencing star formation for eons. So while hypernovae are rare, their legacy is everywhere, in the gold of a wedding ring, the ozone shielding our sky, and the distant light illuminating our deepest cosmic questions. Every white dwarf in the universe walks a tightrope balanced between survival and annihilation by a single, razor-thin number. That number is 1.4, the Chandrasekhar Limit, the cosmic tipping point where gravity overpowers quantum forces and a dying star's fate is sealed. Picture a white dwarf, Earth-sized but with the mass of our Sun, its atoms squeezed so tightly that electrons push back against collapse, creating a fragile equilibrium. Add just a little more mass enough to nudge it past 1.4 times the Sun's weight, and that delicate balance shatters. Electrons can no longer resist gravity's crush. The core implodes, temperatures skyrocket, and within seconds, the entire star detonates in a type Ia Supernova, one of the most predictable and luminous explosions in the cosmos. This revolutionary idea came from a 19-year-old prodigy named Subrahmanyan Chandrasekhar. In 1930, aboard a ship from India to England, he scribbled calculations showing that stars above a certain mass couldn't fade quietly into white dwarfs. His equations defied the era's scientific dogma, which assumed all stars would end as dense embers. When he presented his findings, the backlash was brutal. Sir Arthur Eddington, the era's leading astrophysicist, publicly ridiculed the theory, calling it stellar buffoonery. Yet Chandrasekhar persisted, weathering years of skepticism until observations finally confirmed his limit's existence. Today, his work underpins our understanding of stellar evolution, a triumph of perseverance over prejudice. The Chandrasekhar limit doesn't just dictate stellar fates, it's a cosmic chemist. Type Ia Supernova, triggered when white dwarfs cross this threshold, forge and scatter iron, silicon, and nickel across galaxies, elements essential for rocky planets like Earth. These explosions are so uniform in brightness that they serve as standard candles, allowing astronomers to measure cosmic distances with precision. In fact, it was observations of Type Ia Supernova that revealed the universe's expansion is accelerating, leading to the Nobel Prize-winning discovery of dark energy. But the limit isn't just a passive rule, it's an active player in stellar drama. In binary systems, white dwarfs often siphon gas from companion stars, inching toward catastrophe one stolen mouthful at a time. Some, like the recurrent nova Aristophiaci, teeter on the edge, erupting in smaller explosions as they flirt with the limit. Others, like the progenitor of the famous Tycho supernova of 1572, cross the threshold in a blaze of glory, leaving behind glowing remnants that still echo through the centuries. From shaping the periodic table to calibrating the cosmos, the Chandrasekhar limit is a silent architect of the universe's grand design. It reminds us that even in the cold equations of physics, there's poetry, a single number scribbled on a ship long ago that illuminates the delicate balance between creation and destruction. And every time a white dwarf explodes, it doesn't just fulfill Chandrasekhar's prediction, it etches his legacy into the stars themselves. The universe thrives on an endless cycle of destruction and renewal, where the death of one star becomes the cradle for another. When a massive star explodes as a supernova, it doesn't just vanish. It scatters its essence across the cosmos in a glittering cloud of gas and dust, rich with elements forged in its core. These stellar ashes, drifting through space, eventually coalesce under gravity's pull, forming the nurseries where new stars and planets ignite. It's a process as old as time itself, a celestial echo of ancient myths where firebirds rise from their own ashes or gods die only to be reborn. The difference is, this isn't mythology, it's science, written in the very atoms that make up our world. Consider the iron in your blood or the calcium in your bones. These elements weren't born in Earth's crust or even in our sun. They were crafted in the heart of a dying star billions of years ago, blasted into space by a supernova's fury, and later woven into the fabric of our solar system. Every breath you take contains oxygen atoms that once fueled nuclear reactions in a distant, long-vanished sun. The gold in a wedding ring, forged in the collision of neutron stars, then scattered across the galaxy until it found its way into human hands. We are quite literally made of stardust, a poetic truth backed by decades of astrophysical research. This cosmic recycling shapes entire galaxies. The Crab Nebula, a supernova remnant observed in 1054, is now a bustling factory of new stars, its swirling gases condensing into protostars. Even our own solar system bears the fingerprints of this process. Radioactive isotopes in meteorites' tiny time capsules from the dawn of the solar system reveal traces of a nearby supernova explosion that may have triggered the collapse of the cloud that became our sun and planets. Without that ancient cataclysm, Earth might never have formed. The beauty of this cycle lies in its universality. From the tiniest grain of interstellar dust to the grandest spiral galaxies, the cosmos operates on a principle of transformation. Stars die so that others may live, and in their death throes, they gift the universe with the building blocks of worlds, oceans, and life itself. It's a reminder that destruction and creation are two sides of the same coin, a dance as elegant as it is eternal. So the next time you gaze at the night sky, remember, you're not just looking at distant points of light. You're witnessing a story of resurrection, written in the atoms of everything around you. In the cosmic dance of stellar death, few scenarios are as dramatic or as consequential as the fate of binary star systems. Picture two stars locked in a gravitational embrace, orbiting each other for billions of years until one or both reach the end of their lives. What happens next is a celestial tug of war that can rewrite the rules of stellar evolution. Take, for example, a binary system where one star becomes a white dwarf while its companion remains a red giant. The dense white dwarf, like a cosmic vampire, begins siphoning material from its bloated neighbor. Over time, this stolen matter piles onto the white dwarf's surface, inching it closer to the Chandrasekhar Limit. When it crosses that critical threshold, boom, a type Ia Supernova erupts, outshining entire galaxies and scattering iron and silicon across the cosmos. But the drama doesn't stop there. Imagine instead a pair of neutron stars, each no larger than a city but weighing more than our sun, spiraling toward each other in a deadly waltz. As they draw closer, their immense gravity distorts spacetime itself, sending ripples, gravitational waves across the universe. In August 2017, humanity witnessed this very phenomenon for the first time. The LIGO and Virgo observatories detected gravitational waves from a neutron star collision 130 million light-years away. Seconds later, telescopes caught the aftermath, a kilonova, an explosion so powerful it forged gold, platinum, and other heavy elements in quantities that dwarfed Earth's entire reserves. This single event confirmed what theorists had long suspected, that neutron star mergers are the universe's primary goldsmiths, crafting precious metals in their violent embrace. The aftermath of such collisions is just as fascinating. The merged object might collapse into a black hole, or, if it's just below the critical mass, form a hypermassive neutron star, a fleeting, unstable beast that spins hundreds of times per second before meeting its own demise. These events don't just create elements, they also produce narrow, relativistic jets that can unleash gamma-ray bursts, the most energetic explosions since the Big Bang. One such burst, detected in 2020, originated from a neutron star merger and illuminated the cosmos with light 1,000,000 trillion times brighter than our sun. Binary systems remind us that stellar death is rarely a solitary affair. Whether it's white dwarfs pushing each other to explosion, neutron stars colliding in a blaze of gold, or black holes merging in silent darkness, these duos shape the universe in ways single stars never could. They're the ultimate cosmic collaborators, proving that sometimes the most spectacular endings come in pairs. And as we continue to eavesdrop on their gravitational whispers and observe their luminous aftermaths, one truth becomes clear: the universe's greatest dramas often unfold in tandem. Our sun, that steady golden disk in the sky, may seem eternal, but like all stars, its light will one day flicker out. The countdown began 4.6 billion years ago when this star first ignited, and its final act will unfold on a scale both majestic and devastating. 5 billion years from now, the sun will exhaust its hydrogen fuel, its core shrinking as the outer layers expand into a monstrous red giant. Mercury and Venus won't stand a chance. They'll be swallowed whole, vaporized in a blaze of solar plasma. Earth's fate hangs in the balance. As the sun balloons to 200 times its current size, our planet might escape total engulfment, but its surface will be scorched to a lifeless crisp, oceans boiled away, mountains melted into magma. The once blue marble will become a charred cinder, orbiting a star that no longer nurtures but annihilates. Yet this expansion is just the prelude to a quieter transformation. After shedding its outer layers in a shimmering planetary nebula, the Sun's core will collapse into a white dwarf, a dense, Earth-sized ember glowing faintly with residual heat. For trillions of years, this stellar relic will cool, fading like a dying coal in the cosmic dark. But long before that happens, any surviving humans, or whatever we've evolved into, will face an existential crossroads. One path leads to extinction, the other to the stars. Imagine civilizations of the distant future, armed with technology we can scarcely dream of, watching their home star swell ominously in the sky. They might deploy vast solar shields to deflect the sun's intensifying radiation, or construct orbital habitats beyond the expanding inferno. Some could attempt stellar engineering, siphoning material from the sun to prolong its life, though the energy required would dwarf humanity's current capabilities. The most ambitious solution, planetary migration, using gravity assists or propulsion systems harnessing antimatter. Entire populations might relocate to the outer solar system, where moons like Titan or Europa could become temporary havens in the expanding heat. But the ultimate escape would be interstellar. Generation ships carrying frozen embryos or digitized consciousness could embark for neighboring stars, seeking refuge around younger, stable suns. Alternatively, breakthroughs in wormhole physics or warp drives, though purely theoretical today, might one day offer shortcuts across the galaxy. The descendants of Earth wouldn't just be fleeing, they'd be fulfilling an ancient imperative written in our genes and our curiosity to explore, adapt, and endure. What's haunting is the timescale. While 5 billion years sounds impossibly distant, it's a blink compared to the universe's lifespan. All human history, from the first stone tools to AI and space telescopes, occupies less than 0.0001% of the Sun's total existence. Our star's death will be a slow-motion farewell, but for any civilization witnessing it, the urgency will feel immediate. And that's the paradox. The Sun's demise is both inevitable and, for minds shaped by millennia rather than eons, almost inconceivable. Yet this cosmic deadline carries a strange comfort. It's a reminder that endings drive innovation. Just as supernovas seed the galaxy with the ingredients for new worlds, the Sun's mortality could propel humanity toward futures we can't yet imagine. Whether through planetary engineering, exodus, or transformation into something beyond biology, our response to stellar death might define our greatest legacy. Because in the face of a dying sun, survival isn't just about escaping, it's about evolving. While stars blaze and fade across the cosmos, an even grander fate awaits the universe itself, one shaped by a force so mysterious it makes black holes seem simple: dark energy. Discovered in the late 1990s when astronomers observed distant supernova dimming unexpectedly, this enigmatic pressure now appears to dominate the cosmos, accelerating the expansion of space itself. The implications are staggering. If dark energy continues unchecked, galaxies beyond our local group will eventually vanish over the cosmic horizon, their light stretched beyond detectability. Stars will burn out, black holes will evaporate via Hawking radiation, and over trillions upon trillions of years, the universe may approach a state of maximum entropy, a frigid, featureless void physicists call heat death. Imagine a cosmic graveyard where temperatures approach absolute zero and not a single atom stirs. It's a fate as bleak as it is inevitable, or is it? Not all theories point toward eternal silence. Some cosmologists speculate about a big crunch, where the expansion reverses and the universe collapses back into a singularity, potentially birthing a new cosmos in the rebound. Others ponder vacuum decay, a scenario where a quantum fluctuation creates a bubble of true vacuum that expands at light speed, rewriting the fundamental laws of physics in its wake. Then there's the cyclical universe hypothesis, where each Big Bang arises from the ashes of a previous collapse, an infinite loop of cosmic rebirth. These ideas transform stellar death from an ending into a comma, a pause before the next chapter. Yet the evidence currently favors dark energy's dominion. The James Webb Space Telescope recently confirmed acceleration by studying ancient galaxies, their light warped by expanding spacetime. If this trend holds, even the mightiest black holes will eventually dissipate, leaving behind only a sea of drifting photons too weak to interact. But here's the twist: life and intelligence might still find a way. Futurists like Freeman Dyson once speculated that advanced civilizations could harness black hole energy to survive near eternity, processing thoughts at glacial speeds as the universe cools. Whether the cosmos ends in fire, ice, or rebirth, one truth remains: stellar death is merely the opening act of a far vaster drama. The same supernova that forge elements also seed the universe with the ingredients for future possibilities. And as we peer into the abyss of deep time, we're reminded that endings are rarely absolute, their transformations, woven into the fabric of a story still being written. Beyond the familiar cadavers of stars, white dwarfs, neutron stars, and black holes lies a realm of theoretical oddities that stretch our understanding of matter itself. Imagine a stellar remnant so dense that even neutrons can't hold their form, collapsing into a soup of their fundamental building blocks, quarks. These are the hypothetical quark stars, cosmic laboratories where matter exists in a state unseen anywhere else in the universe. In these extreme environments, the crushing gravity might shatter neutrons into their constituent quarks, creating a swirling sea of strange matter, a form of matter so stable, some theories suggest it could convert anything it touches into more of itself, like a cosmic alchemist's dream. The idea of quark stars isn't just science fiction. Observations of certain ultra-dense objects, like the mysteriously small neutron star Hess J 1731-347, defy expectations. With a mass barely half that of our Sun, yet packing it into a sphere just 12 kilometers wide, it's too light to be a neutron star by conventional models, but fits perfectly with quark matter predictions. Even more tantalizing is the case of RxJ 1856-3754, a stellar remnant whose X-ray emissions suggest a surface so smooth and hot that it might lack a traditional neutron crust, hinting at a quark core beneath. These celestial anomalies challenge our textbooks, whispering that the universe might harbor stranger things than we've dared to imagine. To test these wild theories, scientists turn to Earth-bound experiments. Particle colliders like the Large Hadron Collider smash heavy ions together at near light speeds, briefly recreating the conditions of the early universe, or perhaps the interior of a quark star. These collisions produce a primordial soup called quark-gluon plasma, a fleeting state where quarks roam freely, unconfined by protons or neutrons. While this plasma lasts mere fractions of a second, it offers a glimpse into how matter might behave under the crushing pressures inside these exotic stars. Meanwhile, gravitational wave observatories listen for the faint ripples from quark star mergers, which would vibrate space-time differently than neutron star collisions, like distinguishing a violin's note from a cello's in a cosmic symphony. The most mind-bending possibility: strange matter could be the ultimate Ice 9 of the cosmos, a material so stable that it converts ordinary matter upon contact. If a quark star's core contains strange matter and a fragment broke free during a collision, It could theoretically transform entire planets or stars into strange matter in a chain reaction. Don't panic, no evidence suggests this has happened, and most models deem it unlikely. But the mere possibility underscores how quark stars aren't just curiosities. They're windows into physics at its most extreme, where the rules we know might bend or break entirely. From challenging our understanding of matter's limits to inspiring experiments that recreate the universe's first moments, these hypothetical remnants remind us that the cosmos still holds mysteries too profound for textbooks. Whether quark stars lurk unseen in the dark or exist only in equations, their theoretical allure pushes science to ask, what else might be hiding in the shadows of the night sky? Among the countless black holes lurking in the cosmos, the most elusive aren't the supermassive giants at galactic centers or even the ones orbiting companion stars. They're the rogues. These solitary wanderers drift through the darkness of interstellar space, invisible except for the subtle warping of light around them. Picture a black hole with the mass of 5 suns, adrift in the void, its presence betrayed only when it passes in front of a distant star. The star's light bends around the black hole's gravity like a cosmic magnifying glass, brightening momentarily before fading back into obscurity. This phenomenon, called gravitational microlensing, is how astronomers recently confirmed the existence of one such rogue, the first unambiguous detection of an isolated stellar mass black hole, floating freely some 5,000 light-years from Earth. The discovery wasn't easy. For 6 years, teams sifted through data from the Hubble Space Telescope and ground-based observatories, tracking the telltale flicker of a star's temporary brightening. Unlike black holes in binary systems, which reveal themselves by stealing gas from a companion, rogue black holes leave no trace, no X-ray glow, no accretion disk, just the silent tug of gravity. The newly found wanderer, dubbed MOA 2011 BLG 191, is likely the remnant of a massive star that died in solitude, its supernova kick sending it careening into the galactic abyss. But here's the twist: based on its mass, this black hole shouldn't exist. Most stellar collapses leave remnants closer to 10 solar masses, not 5. Could it be the product of a merger or evidence of a new pathway for black hole formation? The mystery deepens with every observation. Rogue black holes might be more than just cosmic oddities. They could be galactic architects. Simulations suggest thousands of these dark nomads roam the Milky Way, their gravity subtly stirring the pot of interstellar gas, nudging star-forming regions into new configurations. Some might even serve as anchors for dark matter, their invisible halos acting as seeds for future structures. And then there's the existential question: could one drift into our solar system? The odds are vanishingly small, but if it did, we'd notice. Long before it reached Pluto's orbit, its gravity would warp the paths of outer planets, sending comets cascading inward in a celestial domino effect. The hunt for these gravitational ghosts is accelerating. New tools like the Vera Rubin Observatory, set to begin scanning the skies in 2025, will monitor billions of stars nightly, catching microlensing events in real time. Meanwhile, the European Space Agency's Gaia mission maps stellar motions with unprecedented precision, spotting the telltale wobbles of stars tugged by unseen companions. Every rogue black hole found is a clue to the lives of massive stars, the violence of supernova, and the unseen scaffolding of our galaxy. They remind us that the universe's darkest corners often hide its most illuminating secrets. Deep in the halo of our Milky Way, ancient stars drift like celestial fossils, silent witnesses to a universe far younger and more violent than the one we know today. These stellar elders, some nearly as old as the cosmos itself, carry chemical fingerprints untouched by the pollution of later generations. Their atmospheres contain almost no heavy elements, just hydrogen, helium, and traces of lithium, making them cosmic time capsules from an era before planets, before life, even before most elements on the periodic table existed. Astronomers call them Population 3 survivors, though none have been definitively found yet, or extremely metal-poor stars, with metal contents sometimes 1,000,000 times scarcer than our Sun's. The most primitive of these relics, like the star known as SMSS J03 1300 36,670,839, 3, contain so little iron that their composition hints at the very first supernova. Discovered in 2014, this ancient beacon holds less than 1/10,000,000th the iron of our Sun, suggesting it formed from material forged by a single gargantuan progenitor star, one of the universe's first. When that primordial giant died, its explosion lacked the complex elements of modern supernova, leaving behind a chemical signature unlike anything produced by later stars. It's as if we've uncovered a shard of pottery from the dawn of civilization, but one shaped by hands working before the invention of clay or glaze. Mapping these celestial elders is the mission of projects like Gaia, the European Space Agency's star mapping powerhouse. Since its launch in 2013, Gaia has pinpointed over 1 billion stars with unprecedented precision, including thousands of metal-poor outliers in the galactic halo, the sparse, spherical cloud of stars surrounding the Milky Way's main disk. By measuring their motions and compositions, Gaia reveals which stars were born here and which are intergalactic immigrants, captured when the Milky Way cannibalized smaller galaxies billions of years ago. One such wanderer, the star J1835 3259b, orbits backward compared to most halo stars, suggesting it was stolen from a dwarf galaxy long ago. Its composition, rich in carbon but poor in heavier elements, offers clues about how the first galaxies chemically enriched themselves. But the real treasure lies in the rarest of these stars, those with virtually no metals at all. In 2021, astronomers using China's Lomos telescope spotted a star, J0815 + 4729, with iron levels so low they challenge models of early star formation. Its light, analyzed by spectrographs, shows it likely formed from gas enriched by just one or two supernovae, making it a nearly pristine sample of the universe's first stellar deaths. These stars are more than curiosities. They're Rosetta Stones for decoding the conditions of the early cosmos, when the first heavy elements were forged in explosions unlike any seen since. The hunt for these stellar ancients is accelerating. Next-generation telescopes like the Giant Magellan Telescope and the European Extremely Large Telescope will probe even fainter, more distant halo stars, searching for true population 3 survivor stars made only of hydrogen and helium with no metals at all. Finding one would be like discovering a living Neanderthal, offering an unfiltered glimpse into a vanished era. Until then, each metal-poor star we uncover adds another brushstroke to the portrait of our cosmic dawn, reminding us that the universe's past is written not in stone, but in starlight. Among the countless stars that have lived and died across the cosmos, one question lingers like a shadow: where is everyone? This is the heart of the Fermi Paradox, the puzzling contradiction between the high probability of extraterrestrial civilizations and the utter silence of the universe. Could the very deaths of stars hold the answer? Imagine a galaxy teeming with potential life, only for supernova to act as cosmic sieves, wiping out budding civilizations before they can escape their home systems. The same stellar explosions that seed the universe with life's building blocks might also be its most ruthless filters. Take the concept of the Great Filter, the idea that some insurmountable challenge prevents life from progressing to interstellar communication. Supernova fit this theory chillingly well. A single gamma ray burst within a few thousand light-years could sterilize entire swaths of a galaxy, stripping planetary atmospheres with radiation. Evidence suggests Earth itself may have endured such an event. The Ordovician extinction 450 million years ago coincides with a potential gamma ray burst, wiping out 85% of marine species. If advanced civilizations arise only to be erased by their dying stars, the silence of the universe starts to make terrible sense. Yet there's another possibility. What if advanced civilizations don't just succumb to stellar death, but master it? Picture a society harnessing the energy of a white dwarf, using Dyson swarms to capture its fading heat over trillions of years. Or consider the ultimate engineering feat, redirecting a supernova's shockwaves to propel megastructures, or even manipulating a star's collapse to avoid catastrophe entirely. Theoretical physicist Freeman Dyson once speculated that civilizations might migrate to the outer reaches of their systems as stars expand, or even dismantle dying stars to build artificial habitats. The absence of such megastructures in our observations could imply these technologies are impossible, or that we're simply not looking the right way. The debate splits astronomers. Some argue that the frequency of supernova makes the universe inherently hostile, a cosmic game of Russian roulette where only the luckiest civilizations survive long enough to be heard. Others point to Earth's own resilience as proof that life can endure stellar cataclysms, suggesting the Great Silence stems from civilizations choosing isolation or evolving beyond detectable technologies. The truth might lie in the timing. Earth arose late in the universe's lifespan. Earlier civilizations could have flourished and vanished in the era of frequent supernova, their signals lost to time. What's haunting is the implication for humanity. If stellar death is the Great Filter, our survival may depend on escaping the danger zone before the next nearby supernova erupts. Or perhaps the filter is still ahead, a challenge we've yet to face. Either way, the deaths of stars aren't just celestial events, they're existential puzzles, forcing us to confront our place in a universe where creation and destruction are forever entwined. The silence of the cosmos might not be emptiness at all, but an echo of countless stories cut short by the same forces that made them possible. Hidden within the flickering light of stars lies a secret language, a symphony of vibrations that tell the story of their inner lives. This is the science of asteroseismology, the study of starquakes, where astronomers decode the tremors rippling through aging stars like cosmic Morse code. Picture a massive red giant, its surface heaving with waves the size of continents, or a white dwarf pulsing with rhythmic brightness changes as trapped waves bounce between its core and surface. These aren't random flickers, they're precise notes in a stellar sonata, revealing details about a star's density, composition, and even its impending fate. The parallels to music are uncanny. Just as a cello's strings vibrate at specific frequencies based on their tension and length, a star's oscillations depend on its internal structure. Larger stars resonate with deep, slow pulses like the bass notes of a cosmic double bass, while smaller stars hum at higher pitches, akin to celestial violins. The most fascinating cases are the Delta Scuti stars, adolescents in stellar terms, whose rapid pulsations create intricate harmonic patterns. Analyzing these vibrations is like listening to a choir of tuning forks, each one betraying the star's hidden architecture. NASA TESS telescope has become the universe's premier eavesdropper, its sensitive instruments detecting minuscule brightness changes caused by these quakes. In 2021, TESS observed a star called HD 77358, whose oscillations suggested it was far older than previously thought, a revelation that rewrote its expected timeline for becoming a red giant. Similarly, the Kepler mission uncovered star spots on pulsating giants, their surfaces mottled with magnetic storms that distort the quakes like fingerprints on a vibrating drumhead. But asteroseismology isn't just about stellar autopsies, it's a predictive tool. The frequencies of a star's vibrations can betray the presence of helium burning in its core, a sign it's nearing the end of its stable life. In 2019, researchers used quakes in thousands of red giants to map our galaxy's stellar graveyard, identifying regions where stars were most likely to die in supernova. This technique even hints at the existence of exotic objects like quark stars, whose hypothetical ultra-dense cores would produce quakes with frequencies unlike anything neutron stars create. The beauty of this field lies in its universality. Just as seismologists use earthquakes to probe Earth's interior, astronomers now harness starquakes to explore realms no telescope could ever directly see. From the frenetic drumbeats of young, turbulent stars to the slow, mournful pulses of dying giants, the cosmos thrums with a hidden soundtrack, one that's rewriting our understanding of stellar life and death, note by resonant note. Long before telescopes pierced the night sky, humans looked up and saw stories written in the depths of stars. Ancient Chinese astronomers called supernova guest stars, celestial visitors whose sudden appearances foretold earthly events. The biblical Star of Bethlehem, some historians argue, may have been the brilliant flare of a dying star, a beacon so striking it guided wise men across deserts. These cosmic events weren't just astronomical phenomena, they wove themselves into the fabric of human culture, shaping religions, art, and even the rhythms of civilization. Consider Van Gogh's Starry Night, its swirling skies alive with turbulent energy. Art historians note the painting's spirals eerily resemble modern images of gas clouds around dying stars. A coincidence, perhaps, but one that speaks to how stellar death ignites human imagination. The same celestial violence that scatters iron across galaxies also stirs poets and painters, translating cosmic chaos into works that endure for centuries. Even music bears its mark. Gustav Holst's The Planets captures Mars as a bringer of war, its pounding rhythms mirroring the explosive fury of supernova. This cultural legacy runs deeper than metaphor. The very elements that make up our bodies and our world were forged in stellar furnaces. The iron in ancient swords, the gold in royal crowns, the calcium in cathedral marble, all were once stardust scattered by dying suns. Alchemists sought to turn lead into gold, never realizing the universe had already perfected the process in the hearts of collapsing stars. Modern science has revealed what mythologies intuited. We are quite literally children of the cosmos, our existence tied to the life cycles of distant suns. Today, that connection takes new forms. Films like Interstellar visualize black holes with equations penned by physicist Kip Thorne, while sci-fi novels imagine civilizations surviving stellar collapse. Public observatories stream supernova discoveries in real time, turning cosmic death into communal experience. Even our language reflects this bond. Phrases like "reaching for the stars" or "cosmic destiny" reveal how deeply stellar life cycles shape our aspirations. To study star death isn't just an academic pursuit, it's a mirror held up to humanity. In the violent beauty of supernova, we see our own fleeting existence. In the slow fade of white dwarfs, our yearning for legacy, and in the recycled stardust of our bodies, a promise that endings are never truly final, only transformations. The night sky, with its dying beacons, reminds us we are witnesses to a story far grander than ourselves, written in the ashes of stars and the dreams they inspire. From the dazzling fury of supernova to the silent fade of white dwarfs, from the gravitational grip of black holes to the rhythmic pulses of dying stars, each of these 18 perspectives reveals a universe where death is never truly final. We've witnessed how the collapse of a single star can forge the gold in our jewelry, the iron in our blood, and even the silicon in our planet's crust. We've seen how neutron star collisions ring across spacetime like cosmic gongs, scattering precious metals into the void, while rogue black holes wander unseen, their gravity sculpting the galaxy in ways we're only beginning to understand. Each stellar demise, whether violent or serene, is a thread in the grand tapestry of cosmic recycling, where endings are merely the raw materials for new beginnings. Consider the paradox at the heart of it all: destruction as creation. A supernova's blast wave crushes nearby gas clouds, triggering the birth of new stars. A dying red giant exhales its outer layers, enriching interstellar space with the elements future planets and life will require. Even the eerie silence of the Fermi Paradox hints at a deeper truth, that the same stellar deaths threatening civilizations also provide the essential ingredients for their existence. The universe operates on a scale of balance so precise it borders on poetry, where every cataclysm carries the seed of something new. Carl Sagan once said, "We are star stuff pondering the stars," a reminder that the atoms in our bodies were forged in the hearts of long-dead suns. When you look up at the night sky, you're not just seeing distant points of light. You're gazing at a cosmic graveyard and nursery intertwined, where the ghosts of ancient stars whisper their stories in the light of their descendants. Every constellation, every nebula, every flicker of a distant sun carries the legacy of stellar lives lived and lost. So tonight, step outside. Let your eyes adjust to the darkness and take in the vastness above. Wonder at the fact that the same forces that snuff out stars also set the stage for worlds like ours and perhaps countless others. The universe is a story written in stardust, and we're lucky enough to be here to read it. If this journey through the science of star death has sparked your curiosity, share your thoughts below. What part of stellar demise fascinates you most? The explosive, the mysterious, the beautiful. Let's keep the conversation going. And if you're hungry for more cosmic adventures, hit subscribe. We've only scratched the surface of the wonders waiting to be explored. Until next time, keep looking up. The stars have so much more to